Brian, thank you so much. My talk is using machine learning to optimize DevOps practices. I've worked in machine learning for actually quite a while and relatively new to DevOps and looking forward to learning more, which is why I come to these things. I have the obligatory I love me slide here. I speak worldwide on a variety of primarily software topics. I write articles, blog posts. I have a bunch of degrees. At this stage in my career, I consider myself a technology communicator. So I like getting up in front of groups. I like doing webinars. I like writing about things. I am enthusiastic about technology, and I just love explaining it. I'm a former university professor in computer science and mathematics and a technology journalist. And I'm both a cat owner and a distance runner. I'm not sure if those two things are related, but maybe at the end here I'll break out of the presentation and show you a photo of my cats. We all hear about cat ladies. We don't hear about cat men very much, but that's pretty much what I am. Peter at Varhol.com. I will put this up on SlideShare at the end of the day today. So I have an agenda. I'm going to talk a lot about, because what I'm hearing and talking to you folks is I'm hearing a lot of people saying, I don't quite understand what machine learning is in general. So I'm going to talk a little bit about what is machine learning, how are we applying it to DevOps, what are the challenges that we have in training and using these systems, what constitutes an issue, what constitutes a finding within a DevOps context, and I'll try to wrap things up. I have some references at the end that you might be interested in following up on. Oh, I keep pushing the wrong button there. So, I'd like to define machine learning as a set of algorithms. It's a set of layered algorithms in that we feed data points into a set of algorithms. They transform those algorithms transform the data, and we do that in a layered fashion. Sometimes 3 layers, usually at least 3 layers, 4 layers, sometimes you'll see even 5 and 6 layers. And these algorithms can be either linear or nonlinear, and our point is to try to produce an output that successfully replicates the actual problem domain and a possible solution to that problem domain. And the way that we do that is we feed the data into these algorithms, and probably the first time through these algorithms, the result, the output, is probably not going to be very close to the actual result that we're looking for, to the, quote, right answer. And I'd also like to step back and say, there is not, I'll say this a little bit later too, but there is not one singularly correct answer, which makes these algorithms very interesting. Oftentimes, when we think about computers and processing, we think about deterministic processes. We think that for every set of inputs, there is only one set of right outputs. If it's wrong, then we probably have an error somewhere in our code. That's not the way machine learning systems work. Machine learning systems look for an answer that is close to right, close to optimal. And that's what we're trying to do here. So the first time through, those algorithms are not going to produce something that's probably very close to our range of correct answers. So our algorithms will automatically adjust their parameters such that the next time through, hopefully we're closer, and then the next time through with that data, hopefully we're closer still, until we converge on an answer that maybe is not right, but is good enough for our problem domain. And that's what we're trying to do here. I tend to break up machine learning systems into either fixed systems or adaptive systems. And I'll explain a little bit about what that means. Fixed systems, the algorithms normally don't change once the application is deployed. Adaptive systems will continue to adapt in deployment because we're trying to optimize something. And usually also these algorithms are part of a larger system. They don't exist as an application in and of themselves. They're trying to accomplish something specific. So let's take a look at what they might be trying to accomplish. So for example, I live in the Boston area, and I flew in here Wednesday, and I bought my tickets about, 2 or 3 weeks ahead of time or something like that. So I monitor the prices of the tickets over a period of days or sometimes even weeks, because ticket prices, airline ticket prices, change over time. And why do they change over time? What is the airline trying to do? Why do I look at a ticket price and see that it's $400 in the morning and $350? The same exact flight is $350 in the afternoon. What is the airline trying to do? Anyone? What's the airline trying to do here? They're not only trying to fill up the plane, but they're trying to fill up the plane with the highest possible ticket prices. And they do that by changing the ticket prices on a day-to-day basis. So what are they trying to do? They are trying to optimize something. They're trying to optimize what? Well, revenue, profit, however you want to put it, yes. Ultimately, they're trying to optimize their profit. We see e-commerce systems like this too. We see recommendation engines that say something like, you may also be interested in X. And guess what? Sometimes you are interested in X, sometimes you're not. I have an interesting example here. As I said, I'm a distance runner. I have settled on a particular brand of shoes. These are Brooks. These are Brooks Ghost shoes. So I buy, you can't buy the Ghost 8 anymore. I buy the Brooks Ghost 9. So I went on Amazon a few weeks ago, and I typed in Brooks Ghost. And the shoes came up, and sure, I went ahead and I purchased the shoes. And then it said, people who bought this may also be interested in infrared lights, hoods, ghost hunting gear, basically. So guess what? I wasn't very interested in that particular thing. And I'll feel like Amazon. What are they trying to do? They're trying to maximize revenue, maximize what you buy. They're trying to get you to buy more. So even if they're wrong most of the time, if they're right maybe 2 or 3% of the time, guess what? That's a few $1 billion to them. So that's pretty good. So those are adaptive systems. We're trying to optimize something there. I actually had worked on a machine learning system a couple years ago where the subway was looking at changing prices at various times during the day to get to raise prices during rush hours and to lower prices, for example, in the middle of the day or perhaps late at night or something like that. Once again, to be able to, I'll say, smooth out the bumps in their traffic, but also to help fill up their trains and optimize their revenue. So why would you use this? Because the right result will vary. There is no one, there's no converging upon a single set of close enough answers, because that could change over time. So, and as I've been saying, we're trying to optimize a particular result. Our problem domain is not static. Subway ridership, airline ridership is going, airline flyership is going to change at various times during the year. So what we're trying to do is we're trying to adapt to more immediate market circumstances. So how about fixed systems? Fixed systems means that we train the system to a particular set of data because that's going to remain constant. I'll give you an example of a fixed machine learning system that I actually developed and wrote a couple of papers on a while back. And what it was an electronic wind sensor. It was a wind sensor that did not include an anemometer. It had heated coils. And the wind speed and direction was determined by the amount that those multiple coils were cooled when the wind was blowing. So I had data on the temperature of each of the wind systems, and we tested this in a wind tunnel. So we had data on what the wind speed and direction was as those systems cooled. So, and then I came up with a system that did not completely accurately replicate the wind speed and direction or predict the wind speed and direction, but I came up with a set of algorithms that was close enough. It was like wind speed within 1.5 knots or something like that, and wind direction within 2 degrees. So we also see this in self-driving cars and in aircraft and pilotless aircraft drones. We also see this in, for example, medical diagnostic systems, because diagnoses do not change over time. We've got expert systems, we've got learning systems that are looking at x-rays, blood test results, MRIs, things like that, and trying to come up with a single fixed diagnosis. And that's where we see fixed systems. Both of these types of systems, I should say, likely have applicability for DevOps practices. So once again, the problem domain is static, our expectations remain constant. The right answer is known, and the original algorithms will remain correct over a long period of time. So in DevOps, as all of you know, we generate lots of data. During development, we have agile metrics, burn rates, Jira issues, test case metrics, integration, continuous deployment. I'm most interested at this point in focusing on deployment and after deployment and into production. I'm interested in looking at application availability and performance, usage log files, the variety of data that we can collect on an application once it's in deployment. We had a couple of people talk about MTTR, mean time to repair or mean time to remediation, however you might want to word that. But what we're looking at is we want to look at how these systems behave after they go into production. We probably already have a lot of tools doing that. We probably have we might be using Splunk, we might be using Symologic log files, we might be using my old friends at Dynatrace, that type of availability and performance metrics. And we have a lot of that data. We may have multiple tools. Chances are we are using multiple tools, and that's a lot of data. So we're generating a lot of data. As I said, I'm interested in focusing on monitoring. We have real user monitoring, synthetic tests, application monitoring. It tackles looking at things like identifying trends that we may be able to focus on as perhaps being unhealthy, diagnosing failures and poor performance. Why did this happen? And also possibly recommending action. We have seen this before, and before you took X corrective action and it worked. So you might want to try X again. So we're also interested in doing predictive analytics. We want to look at what are we seeing now that might make it possible for us to predict what's going to happen in the future. Are we going to fail? How are we going to perform as our traffic surges or lessens or comes from different parts of the world? So also we want to focus on past events, what went wrong, how can we possibly fix it? And we want to look at past data, both fixed systems and saying, this is what happened in the past, we recognize this, and can look at what we can do when this happens again. We may actually look at adaptive systems for optimizing performance, optimizing availability, and things like that. So what are the technologies involved here? You've probably heard several of these terms, and I'll just run through this fairly quickly. Neural networks, genetic algorithms, and rules engines. So the neural network is what I just described here. We've got a set of layered algorithms where we're feeding in data. Those algorithms are transforming that data to produce a result. And we keep on running known data, known inputs, and then comparing what that algorithm produces for outputs and comparing that to the known correct output. That process is known as training. And so what we're doing is we have data, we know the result that we're looking for, and we just keep on running this training data through the system until we get answers that are close enough. Then we freeze those algorithms. They say we don't have to change anymore. We don't have to change those algorithms anymore. So this is a sample neural network where we might input 3 data items into an input layer that has a set of algorithms, linear or nonlinear. We use 1 or more hidden layers to further transform that data and in order to produce perhaps a couple of different outputs, depending on what we're looking for. Genetic algorithms work in a somewhat similar way, but generally we have a collection of algorithms, and we run our data through them once, and we see what kind of results they produce. We choose 2 of those algorithms and make them together, so to speak, in the next series of, in the next generation, and then we look at those results, and hopefully, eventually, perhaps after dozens of iterations, they converge upon the solution that we're looking for. So let's go back to DevOps here. We have plenty of data that we can use to train neural networks. We know what our data looks like when we have failures. We know what the characteristics of our performance is under a single user, under load, under things like that. So we have also trends in application traffic and the location of that traffic and the amount of that traffic and the responsiveness of our application. And then we know what our application looks like when it fails. So our decisions are complex. What we're trying to do is we're looking at problems like, why is our CPU maxed out here? What is causing this disk thrashing that I'm seeing? Why did the network slow down dramatically all of a sudden? And probably the big one, the holy grail, so to speak, is why did this failure occur? Because if I have data on why this failure occurred and what the system looked like, what the system in the network looked like when failure occurred, I may be able to A, predict a failure when a failure is coming in the future, and B, if I have the failure and know the right answer, know the solution, be able to apply that solution much more quickly. So how good are the decisions that are data-based versus expert-based? Because we have people in our data centers who have seen it all. And how do they compare against some of the expert systems, the machine learning systems that are appearing today? Given the same data, generally speaking, the machine learning system will do at least as good as the expert. And that's what the systems that we have now are producing. The expert can be better if the expert has information or data that is not included within the machine learning system, but in general, our machine learning systems are at least as good as the expert in diagnosing and offering recommendations here. But it's only as good as the data. So we're trying to identify trends that may indicate future problems. Are we seeing increased response times based on perhaps where the traffic is coming from, how much traffic? Are we seeing more page errors? And then once the fault has occurred, we'd like to diagnose and offer remediation. Fixed algorithms work for some of these problems, but adaptive systems can also supplement the fixed algorithms. So you may be actually looking at multiple machine learning systems, those that where you're looking at the same result, you know what the result is, you know what the data is going to look like, and you know what result that you're looking for is. But adaptive systems can help us do predictive analytics better. So we can get, as a result, we can get early warning on possible performance issues, failures. We can look at immediate notification of failure, perhaps an impending failure. We can look at trend analysis too, to see what might be occurring, whether it be some combination of CPU, disk, network access, network performance, and things like that, to predict unhealthy outcomes. I'd like to emphasize, however, that the machine learning system is an assistant. It's not there to do your job for you. You're the one that's going to have to make the decision, and you're the one that's going to have to implement solutions. It's not going to fix anything, and it can't necessarily identify what your root cause is. That's where human expertise supplements the machine learning assistant. So we have many ways of monitoring. As I said, we have sumo logic logs, we've got Splunk data, we've got whether it be New Relic, Dynatrace, whatever it is, they're all looking at something. They're all collecting tons of data. That data is a little bit different in almost all cases. And in that case, we may be looking at latency, response time, availability, so on and so forth. And sometimes there are times when too much data, if we have too many of these systems, is no better, and it can be worse than having no data at all. So these machine learning systems can actually take a lot of that data if we train them correctly, whether we purchase a commercial machine learning system to look at this data, or whether we write our own expertise in-house. These aren't terribly difficult to develop. So either way, the machine learning system can look at data from a variety of sources and come up with correlation that even the human expert cannot do alone. I'd like to offer a couple of cautions here. Our problem domain is ambiguous. Sometimes we never find the root cause to a particular class of problems. There's no single right answer either. Sometimes the answer, even for similar data, may be subtly different. And we don't know why the machine learning system produces the results that it does. We're talking about the possibility of applying dozens of linear or nonlinear algorithms to this data, to maybe thousands, hundreds of thousands of data points at a time. So it can be humanly impossible to actually trace the code paths and determine why a particular result is achieved by the machine learning system. So how do we test these? I have here a laundry list. We need, if we're going to test a machine learning system, we need objective criteria, but we also need to understand that we're looking for a range of possible solutions rather than a particular type of solution. We're not looking for the one right answer. We're looking for an answer that is good enough to get us over the hump that we're at right now. We need to, even at the DevOps level, we need to understand at a higher level what the machine learning system is doing. And I make the point on the next slide, actually, that I attended a presentation about a year or so ago where the speaker made the point that you can't automate something that you don't understand. If you can't do it yourself, now granted, you may not be doing it as efficiently as a machine does. You may not be looking at all the data like the machine does. But if it's a problem domain that you have no expertise in, then you can't effectively use the results you get from the machine learning system. Does anybody remember, I think this was about 2014, maybe even before that, there was an Air France flight flying from Sao Paulo, Brazil to Paris. And it went down in the middle of the Atlantic in a severe thunderstorm. What happened was that within the context of the severe thunderstorm, the junior pilots, the captain had gone back to the crew rest area. The junior pilots who were flying the plane did not understand the instruments were. They did not understand the instruments were wrong, and did what the instruments told them to do. And in doing so, what they did was their airspeed was slowing, and rather than descending to increase their airspeed, they started climbing. They started climbing to such an extent that the aircraft stalled out and literally fell into the sea. And that's because they relied on the instrument data rather than relying on their own aviation and piloting knowledge. And that's what we as DevOps professionals have to do in order to effectively use machine learning systems. We have to rely on our expertise and the expertise of those around us. These are assistants, folks. They're not the be-all and the end-all. I have another one. I grew up in the Pittsburgh area, and I'm of a certain age, so I remember being about 12 years old in the 1970s and going to Forbes Field. Does anybody ever heard of Forbes Field in Pittsburgh? It was the Pittsburgh Pirates baseball stadium until I think the late 1970s. So I remember going to Forbes Field. I remember it's the bottom of the ninth inning, and the Pirates are down by 1 run. They have a runner on first, and there's 2 outs in the bottom of the ninth inning. They have a runner on first, and Roberto Clemente steps to the plate. You may have heard of Roberto Clemente. He's in the Baseball Hall of Fame. And he was a very good fielder. He was a very good right fielder. Also was a very good hitter for average, but was not a home run hitter. So he stepped up to the plate, and he hit a walk-off home run and won the game for the Pirates. I think this is in one of their World Series years in the 1970s. And he hit a walk-off home run. What did Roberto Clemente do there? He did something that was uncharacteristic of him. I shouldn't say uncharacteristic. Well, he hit a home run, which was uncharacteristic. But he delivered in the clutch. He, as an athlete, recognized the gravity of the situation, recognized the importance of him delivering in the clutch, and did exactly that. So I'd like to draw that back to people can deliver in the clutch. Machines can't. To a machine, all events are created equal. When in real life, all events are not created equal. We may have a failure, have unhealthy trending at a critical time for our application. It may be the holiday season, and we need to book the revenue that consumers are bringing on our site, the increased sales, whatever it might be. The system, however, treats all the events equally. We know otherwise, and we as DevOps professionals can respond appropriately when the situation calls for it. And actually, we can expend that additional effort and actually identify and fix the problem. We can work overnight. Now, granted, the machines work overnight too. But once again, the idea is that they don't understand when that sometimes are more important than others. Some problems are more important than others. Some solutions require extra effort. And once again, I say that we can't automate what we as professionals don't understand, and that's why we need the human in the loop. So just to wrap this up, I think the DevOps, especially the monitoring aspect, and I think we'll see it used, we'll see machine learning used elsewhere within the DevOps context too. But it's a natural environment for machine learning systems. Anytime that we're generating large amounts of data, we're able to design a system to help us understand that data and analyze that data and come up with a solution. Fixed systems for things like diagnosis, for failure in diagnosis. Adaptive systems are more appropriate for trend analysis, looking for unhealthy trends and things like that. So I have some references here, and like I said, I'll put this up on SlideShare. So just search for me. I'll put this up tonight. So just search for me on SlideShare, and a couple of them are my own blog posts. One of them talks about using machine learning systems in a medical context also. So otherwise, thanks for your attention, and I'm not going to stand in the way as you stream out the door for lunch. Thank you.